second reaction in the triple H series is the Hoffman rearrangement. And the Hoffman rearrangement, recall, takes an amide. It only works on primary amides. Because it requires two protons that can be removed on nitrogen for this mechanism to occur. And generates a primary amine as a product. Along with CO2 gas from the carbon that used to be the carbonyl-carbon. So we're going to form a bond from this carbon to the nitrogen. And it turns out that that goes with retention of stereochemistry. So if this were a chiral center, make it a chiral center simply by replacing one of those hydrogens with deuterium. The hydrogen and the deuterium would be in the same position in the product. So the reaction involves bromine and a base. Often hydroxide. Hydroxide is going to take off the most acidic hydrogen, and it has a choice between the hydrogen on the alpha carbon and the hydrogen on nitrogen. Both of the anions created by removal of those hydrogens would have resonance stabilization, but this one also has the more electronegative nitrogen. So the pKa of the hydrogen on the NH2 group is about 22, whereas the pKa of the hydrogen on the carbon is about 30. You'll notice that this is actually a higher pKa than the pKa of the ketone. So if we look at the pKa of the acid chloride, or bromide in this case, the acid halide, that one was about 16. The pKa of a ketone, or an aldehyde, is around 20 to 22. pKa of the ester is around 25. And the pKa of the amide is around 30. But only if the amide is tertiary is it possible to form an enol of the amide, because the nitrogen hydrogen, or the hydrogen attached to nitrogen is much more acidic. So that one's going to be removed preferentially, right? Remember we said you can't make the enolate, you can't make the enol, rather, of the carboxylic acid either, because the pKa here is 5. So you're never going to take that one off. Only if there's no acidic hydrogen on this other side can you remove that. So as you might expect, the more the carbonyl carbon is stabilized by forming a double bond to the atom with a lone pair, in this case the nitrogen, in this case the oxygen, the less acidic the alpha hydrogen becomes. Because if the lone pair on the nitrogen is already participating in resonance, then the negative charge on the alpha carbon can't participate in resonance. Nitrogen is less electronegative, therefore it forms a larger contribution from the resonance structure that has the carbon-nitrogen double bond than there is for oxygen, rendering that acidic hydrogen less acidic. And since bromine makes very little contribution because of the 4-orbital overlap, the alpha hydrogen is more acidic. Actual resonance that you can have when you have a lone pair of this adjacent atom form a carbon-nitrogen double bond or a carbon-oxygen double bond is more important than hyperconjugation, which is the donation from one of these carbon-hydrogen sigma bonds into stabilizing the pi system. So the more resonance you have, better. Nitrogen has more resonance than oxygen. Any resonance is better than hyperconjugation. And then here, the resonance contribution is very poor because of the orbital overlap, but the electron withdrawing bromine causes this to be even more acidic than it would be if you had an electron donating. All that is kind of, as an aside, point out that the first step of the Hoffman rearrangement is going to be to remove the acidic amide hydrogen. Create a negatively charged nitrogen. And I guess we're going to continue to show that chiral center. Resonance stabilized. The more important resonance structure is, in fact, the one with the negative charge on the more electronegative oxygen. But as is usually true in organic chemistry, the less significant resonance contributor is the one that explains the activity. Because the next step is going to be that negatively charged nitrogen attacking bromine. Deprotonation at the amide nitrogen. And step 2 is going to be the anion attacking electrophilic bromine. So what we've done is we've brominated on the alpha position. And because this is under basic conditions, we've brominated it by deprotonating, followed by the attack on the electrophile, much like making an enoate ion, right? This is not quite an enoate ion, but it's very similar to an enoate ion. And it behaves the same way as an enoate ion. So the Helmholtz-Zielinski reaction under acidic conditions proceeds through the enol tautomer, but the Hoffman rearrangement under basic conditions proceeds through the equivalent of the enoate ion. This is now even more acidic than it was to begin with because of the electron withdrawing bromine. So hydroxide can take that hydrogen off to make a new enoate ion. Negative charge on the nitrogen again. We saw this same situation when we were brominating alpha to a carbonyl group in an aldehyde or a ketone, in that the carbon-hydrogen bond became more acidic after we put the first bromine on there, which made it impossible to stop at just one bromine. The difference is that now, instead of this attacking another bromine to put a second bromine on the nitrogen, bromine just leaves as bromine ion. that generates an electron deficient species that is neutral. That has an unfilled orbital and lone pair at the same time, called a nitrene. And the nitrene is analogous to a carbene. There's a lone pair and an empty p orbital on the same atom. And that atom is neutral. In this case, it has two lone pairs because it's nitrogen rather than carbon. That's unstable. It doesn't like having an unfilled octet. So what happens next is the alkyl shift, where this carbon-carbon bond will simply migrate over to the nitrogen and remain neutral by pushing a pair of electrons from nitrogen into form a carbon-nitrogen double bond. That's the key step. Alkyl shift. And like the alkyl shift in the oxidation step of hydroboration, it goes with the tension configuration and generates a functional group with a carbon nitrogen and a carbon oxygen double bond, which is an isocyanate. The carbon that's between those two has a large particle positive charge on it and is then attacked by hydroxide ion. And you can push the pair of electrons onto either the nitrogen or the oxygen. Push it onto the nitrogen. And what we're making here now is a carbamic acid. By protonating nitrogen carbamic acid, where we have an OH, we have a carbonyl group sandwiched between an oxygen, has an OH group and a nitrogen. Carbamic acids are unstable. And we'll eliminate CO2. And we can make that go through a 400 ring. And with 6 electrons floating in that ring. Last step, 8. Loss of CO2 gas. That's not reversible. Because the CO2 gas escapes. So the key step is that alkyl shift. It's occurring in step 5. And then the isocyanate, right? So we have the nitrene at the end of step 4. We have the isocyanate at the end of step 5 after the alkyl shift. And we have the, I think we need to erase that. Stay there. So the nitrene is a key intermediate at the end of step 4 after bromide leaves. The isocyanate is a key intermediate at the end of step 5. And the carbamic acid is the key intermediate at the end of step 7 after the nucleophile is attacked by hydroxide and protonation from water. We have a final decomposition. So it's less complicated than the Hoffman reaction, but it goes through some interesting intermediates.